It's the Life Upfront Engineering Podcast. I'm your host, Jeff Waters, covering ideas, people, and products on the cutting edge of product development. As always, join the conversation at lifeupfront.com. Today on the show, an obscure engineering author, Kickstarter, technology evangelist, and entrepreneur, president of the one-year-old Exogeny Inc., and president of the North America Modelica Users Group, Michael Tiller. Michael, welcome to the show.
Hi, Jeff. Thanks for having me.
So my listeners may not be super familiar with Modelica. Can you start with a high-level sort of Modelica for Dummies description?
Wow, Modelica for Dummies. Let's see. So Modelica is a modeling language, and that distinguishes it from most other computer languages that you're probably familiar with because it's really a language for posing mathematical problems. But one of the things that it does is it borrows on a lot of ideas from modern programming languages, this idea of object-orientedness or inheritance or encapsulation, reuse, configuration management. So what happens is in complex engineering systems, we actually have a very object-oriented nature to these things. You have, you can think about just an electrical circuit as an example. You have a resistor, capacitor, some voltage source. So you have these objects and they're connected together. Now, they don't actually run code per se. They're not. It's not what you'd call from the computer science side an imperative language, which is to say a language that's made up of instructions of saying do this and do that, and then do this and then do that. So that's what most general purpose programming languages like Java or Python or C are like. Instead, it's a language that features the object-oriented nature of a lot of languages and inheritance and encapsulation and things like that, but really for the purpose of building up a set of mathematical relationships between components. And these mathematical relationships can be continuous relationships like algebraic equations or differential equations, or they can be discrete kinds of behavior. So this is typical in discrete control kinds of applications. You imagine just like the thermostat in your house. It kicks on at a certain temperature and then it kicks off at a certain temperature. So you have discrete kinds of behavior as well. And so it's a language that basically at its lowest level allows you to describe these continuous and discrete kinds of behaviors. And then using the high-level features in the language, you can wrap those up into reusable objects that you can then compose by connecting them together.
So to put this into a real-world context, just pick some kind of a real-world system.
Sure. So a really good example, I think, is a transmission, an automotive transmission. So if you look at an automotive transmission, you would have at the top level, of course, a transmission. Now, if you think about in the U.S., typically we have automatic transmissions. So in an automatic transmission, you might have a torque converter. Well, you almost certainly will have a torque converter in the sort of the front side of the input side of the transmission. Then you'll have a gearbox. Then you maybe have a final drive ratio. And then depending on where you draw your boundary with the transmission, you might include the half shafts that go out to the hubs on the tires. So the thing is, there's a couple of things you can do in Modelica that are interesting with an example like this. The first thing is you can build up an architecture to say, well, I'm going to build a model of an automatic transmission. It's going to have a torque converter and a gearbox and maybe a drivetrain at the end of it, but I'm not going to say what those things are. And this is very common even in software where you do when you build up systems, you can use this idea of abstractions to say, well, I don't know exactly, the typical example from a programming standpoint would be things like, well, I have a list of shapes and I don't know if they're circles or squares. You have this, what's called polymorphism goes on there. You can say, well, shape can be anything. It could be anything that has a perimeter and an area, but we don't know whether it's a circle or a square or a triangle. You can kind of do the same thing in the modeling world. You can say, well, okay, what's a torque converter? Well, a torque converter is something that has an input shaft and an output shaft and generally has a bypass clutch. And beyond that, there are different models. There are some models of torque converters that take into account the inertia of the fluid spinning inside of them. There are other ones that are just simply steady state models. But when you build up the architecture, the only thing that you're concerned about is to say, well, I'm going to put something here in this slot that says torque converter that I can connect to the input shaft of the transmission and then connect on the output side of the torque converter to the gearbox. And I'm going to need some kind of control signal to turn the bypass clutch on and off. I don't care beyond that what's inside of it. And so I have the freedom to swap in different implementations of that torque converter, different models of that torque converter depending on what kinds of physical details I'm interested in. If I'm doing a simple something like an EPA drive cycle test, normally you use a very simple torque converter model. If I'm looking at shift quality kind of application where I'm interested in the vibrations that the driver perceives due to torque fluctuations on the drive line or even seat track acceleration, then I'm going to have a different model in there that's going to have a little more of the hiccups and bumps and things like that that go on during a shift. So the nice thing about this is it takes a lot of ideas from the software world about abstractions and polymorphism and applies them to this physical modeling context, which allows you to engineer some complex systems, but also with a lot of reuse between applications, that you're not constantly reformulating equations and reworking your system. You're just able to use this sort of a la carte, fill in the blanks kind of approach to a lot of model construction, save some time that way.
So when you're talking about a Modelica based tool for a transmission, the listener here shouldn't be envisioning a 3D model or some sort of FEA analysis of spinning parts interacting with each other. It's much more like an earlier phase schematic, or a 2D block diagram with 1D math models representing a black box of each one of those components you were talking about.
Yeah, exactly. I mean, in fact, if this were a video podcast, I'd have a figure popped up here to show you, but let me try and paint this picture, nevertheless, in your mind. So the thing is, if you look at the system engineering V, I mean, at least this is the way I look at it. You look at the system engineering V, you have the design side right on your way down, and you have the validation or verification side on the way back up. Now, so you're cascading requirements down on one side, and then verifying requirements on the way back up. So what happens, what's interesting to me is just to understand the landscape of these kinds of things you mentioned, like finite element stuff and CFD. So to me, the distinction here, where it really becomes important, is when geometry starts affecting behavior, right? So the way I usually draw this, I draw this V, and then I draw a line across the middle of it. And I say, okay, at some point, and it depends on the subsystem, it depends on the application area, it depends on a lot of things, but at some point, 3D geometry becomes important here. So you can get away with these kinds of 1D models that I'm talking about for Modelica at the top of the V for sure, on both the design side and the verification side. So that's no problem. So on the design side, you might be doing things like architecture studies or just using high-level models to cascade requirements to lower-level subsystems and components. On the verification side, you might be using them to do things like hardware in the loop studies and do controller validation and stuff like that. But in any case, they're above this 3D geometry line. Below this 3D geometry line, you tend to have the CAD and the finite element kinds of things going on. So their geometry is important. So all the chamfers and fillets and and all that stuff is there in its detail. What's interesting is how to bring these two things together. So when I deal with the engineering process, I have to face this gap here. And what it really boils down to is you can use these kinds of 1D models, the Modelica kinds of models, to help you generate things like loads for these finite element models, right? So the idea is, if you go back to this transmission example, the question is, so the input shaft of the transmission, what kinds of torque does that actually need to be able to sustain? And you would think that you have these sorts of rules of thumb. Oh yeah, we've been building cars for a while, and so what's going to happen is it's we know that for an F-150, the kind of torque that comes out if you have a 8-cylinder engine is going to be this much, and we know a little bit about how we've done vibration isolation. So even though the engine might spit out really large peak torques, we know that there's some isolation elements between the engine and the transmission, and those will reduce it down. And so, sort of rule of thumb, it's going to be this. And I saw I've seen a couple of really interesting examples of where this breaks down, because now we're sort of experiencing this automotive renaissance, I think, where all kinds of interesting technologies are suddenly popping up that really weren't there before. You have electric vehicles, you have series hybrids, you have hybrids like the Ford Escape, which is a sort of hybrid. Strangely enough, it's a parallel and series hybrid. And what's happening is that there's a lot of technologies that are coming into play here that change the conventional wisdom. So you end up, for example, with a lot of these electric vehicles, you end up with electric motors involved in the powertrain at some point. And these electric motors have a very large rotating inertia. And you need to sort of go back to square one and say, okay, so given that we have this really large inertia here, what does that say about the kinds of torque profiles we're going to get on the various the powertrain components? And you have to be able to do that analysis. And as you innovate and come up with new kinds of topologies for drive lines, you have now there's a whole new kind of transmission that a lot of people are working on, which is a dual clutch transmissions. Same story. I mean, it's not hybridization per se, but um, it changes the conventional wisdom. You have to be able to go through and do those kinds of analyses, and then be able to feed good boundary conditions or loads into your low-level finite element and CFD tools, because otherwise you end up either over-designing or under-designing and not knowing
Yeah.
that you're doing that.
Yeah. Yeah. Well, when we start describing because I had a chance to try to describe how, what these tools are and how they work. When you go out and start talking to companies and you're describing this to people who aren't directly involved in it today, I think what you're likely to hear once they get, oh, okay, we're talking about 1D models, we're talking about block diagrams, we're talking about, the high level simulation. They say, okay, yeah, we already do that. It sounds like Simulink. And I think Simulink is pretty much ubiquitous because they have such a huge footprint in academia, at least here in the US.
Mm-hmm.
And, most mechanical engineers, if they went through a controls course in the last 10 years, probably played with Simulink at some point. So how is this different? I mean, why not
Well,
just use Simulink?
yeah. So the thing is, you make a good point. You said it yourself. You said most mechanical engineers, if they went through a controls course, use Simulink, right? And that's the thing, is that Simulink and the whole MATLAB platform and Simulink in particular are really excellent tools, and they're really they're well developed, and they're targeted at meeting customer needs. The problem you have is that they're mostly targeted at meeting the needs of people who are developing control systems. Now, for sure, if you're developing control systems, Simulink is a great tool. I mean, I'm not really in the space of developing control systems, so I don't really know exactly how they compare to their competitors. There are other technologies out there, but for sure, I look at the Simulink tool set and I think this is a really nice tool set if I'm developing controls. The problem that you have is sort of this, when you have a hammer, everything looks like a nail kind of thing going on. If you're developing controls and you have relatively simple needs for building dynamic systems for your plant, right? So when you're doing controls, I mean, in case, for people who might be listening who aren't sort of up on this area, when you develop controls, the purpose of the control system is to control what's called a plant. I don't know where it got this name. It sounds like a name from the 1950s for sure. But anyway, the idea is that there's some system, whether it be a car or an airplane or a nuclear power plant or whatever. It's just called the plant. So the plant is the physical thing, and the control system is what's controlling the inputs to it and trying to achieve some ideal output, right? So in this case, if you're a control system engineer and you have relatively simple needs for modeling the plant, which is to say the thing you're controlling, then you can sort of kill two birds with one stone by using Simulink to model both the controls and the plant. The problem comes as the plant becomes increasingly complicated, or when you're involved primarily in designing the plant and are not really involved in the control aspect. So there are a lot of limitations in a tool like Simulink. The biggest one that I always point out to people is that in Simulink, just in case people aren't familiar with Simulink, the basic idea in Simulink is that you take the mathematical equations for your system, and they can be differential equations, algebraic equations, and you have to then first start off saying, okay, well, I know these things. Like I know the torque, or let's say I know what voltage this battery has, and so I know that. Then I can look at this resistor, and given that I know the voltage, I can then calculate a current, and then that current maybe goes through two different paths, and one goes into a capacitor, and so I integrate the current to calculate the change in the voltage over the capacitor. So the point is, in this case, you start with all the things that are known, and then you sort of gradually work your way through and say, well, if I know those things, then I can compute a few more things. And then if I know those few more things, then I can compute a few more things. And you just go through this process until you get to all the things that you want to compute. They all get computed then. Now, the problem with this approach is its scalability. That when you suddenly decide to, if you have a fixed set of components that you want to simulate, your system, and you decide that, well, in this particular case, I switch so that I don't know the voltage anymore, but I know the current as an input. So, okay, the set of things that all the assumptions you started with at the very beginning have changed. So now I have to go through and reformulate all of these things again. And there's a lot of essentially math and algebraic manipulations required to do this. So the way I describe this for people is that it's really like doing long division. It's really, I mean, if you think about it, when you do long division, you write down two numbers, you divide one by the other, you have to do a bunch of multiplications and then some subtractions and then more multiplications and subtractions, and then you get your number at the end, your output. But if you change any of the two inputs, any of the two numbers that you started with, well, okay, you got to start all over again. You got to do all that math in between. And the problem there is not so much that I have anything against math. I love math. But frankly, those kinds of things have three really bad properties if you're running a business. They're tedious, they're time consuming, and they're error prone. And those are three things you're trying to get rid of, right? And so what would be nice is if you had a method for building up these systems where when you changed the fundamental assumptions that's, at the start of this, that you didn't have to worry about the time and the potential for error that comes in doing the transformations to get to those outputs again. It would be nice if there were a way to sort of automatically get through it, much like you have with a calculator. You punch in the numbers and you reliably and quickly get an answer, and you don't have to worry about some sort of middleman there making a mistake in doing some hand calculations to get between those two things. And so that's really what Modelica brings to the table, is this ability to take an equation like Ohm's law, put it into a resistor component model, and bookshelf it. And when you need a resistor, you pull it down. And it turns out in Modelica that whether you use Ohm's law as V, is I equals V over R, okay, you could use it that way, or you can use it as V equals IR. It doesn't actually matter. It's a mathematical equation in Modelica, and so the tools themselves can treat it as an algebraic relationship, and they can do those manipulations that you would otherwise be doing of transforming the equations into a form where they're solving explicitly for one variable in the equation given all the other variables in the equation. So that's all part of the symbolic manipulation that gets done behind the scenes in these Modelica tools. And so it's essentially cutting out that tedious, time-consuming, and error-prone step in building up these kinds of models.
Yeah, so Modelica is still relatively unknown. Maybe that's not the right way to say it. It's not as popular.
Well, in the U.S.
In the U.S., it's not as popular, mainly because it started out of some European universities, particularly in Sweden. And, it's very popular over there. I'd say in industry even, it's a lot more widespread usage. And, people do like it. Like once they start using it, they immediately see, oh, this is great. We can create this component, like you said, put it on the shelf. We know it works. And hey, we got this completely different system over here. And maybe the inputs to that particular section of the model where you want to drop this in are the reverse of what you had when you created the model. It'll still work. And that doesn't work for Simulink.
Right. Yep.
Yeah.
And you also, I want to go back to one thing that I was, mentioning before, which is this idea that you have all these innovations. You have hybridization. You have dual clutch transmissions, things like that. One of the things I found when I was first working with Modelica, I was at Ford at the time, and one of the things we found was that as we were going through this hybridization phase, so this was around 2000, and we were working on the Ford Hybrid Escape. Essentially, what happened was as the company shifted to a cycle plan that involved these new technologies, so things like hybridization, it created some significant vacuums in the tool sets that we had. And the fact that we could, and the real saving grace of Modelica in that context was that we could very quickly build up models. There wasn't a lot of this tedious, time-consuming stuff. We could just build the models and combine them and compose them really quickly. And it was also extensible, right? So it's not just the fact that you can sort of drag and drop a bunch of bookshelf components together and compose them. It's the fact that you can make your own components. So that's another thing that distinguishes it from some of the physical modeling tools that are out there, the plant modeling tools that are out there. is the fact that some of them will give you a bunch of black boxes, and you can drag the black boxes down and connect them. And sometimes there are special rules about how you can connect these things. But in general, Modelica is built on this principle of openness and extensibility, that you can build any model that anybody else can build. The vendors, the tool vendors, don't have any inherent advantage in building these things. And so
Other than their expertise.
well, sure, but thing is, they don't have, assuming you have that expertise, then you're on equal footing, right? There's no backdoor special APIs or anything like that that they're using to implement the things that they want to implement. If you look at the Modelica standard library, for example, which is a standard library of components written in Modelica so that people don't have to constantly reinvent their own resistor and their own spring and their own inertia and things like that. I mean, it's an open source project. You can go in and you can see all the source code, and it's not just that source code isn't just like documentation. No, it's the real source code that's used when those models are compiled. And you can take that source code and make your own component model, and it'll behave exactly like that component. But then you can change it and you can enhance it, and you can say, oh, well, what happens if I want an inertia that has that changes with time? Well, then I have to change the equations, so that I get a term that's associated with the change in inertia as a function of time. So you have all of these possibilities that are open to you because it's extensible. You can create your own stuff. And so, getting back to my original point, the thing is, when you're facing this sort of these kinds of technological and innovation shifts that you see, fortunately, in the automotive industry, but you're pretty much seeing it everywhere. I mean, it's part of the competitive nature of these markets, is everybody's trying to build a better product, and a lot of that is coming up with new ideas. And so you see a lot of this in the automotive sector. And my point is that tools like, or technologies like Modelica, are going to allow you to quickly fill those vacuums in ways that, as I said, are automated and quick, fast and relatively error free. And so that creates essentially a demand for these kinds of capabilities. If you're just doing the same old thing, just running drive cycles on conventional vehicles, or with standard sort of powertrain topologies, there's a lot of sort of entrenched tools that you can use there. But if you're in an area where there's a lot of innovation going on, these technologies are really a big advantage.
Now, so you were involved with Modelica back in 2001, at least, at Ford, 2000 and Ford. And today you are the president of the North American Modelica user group, as I said at the top of the show. So you're pretty passionate about this, and you've been at it for a very long time. So I'd say you're one of the leaders in the world of Modelica. In fact, you literally wrote the book on Modelica. So I think it was maybe the first one out there, but
it was, yeah.
Yep, released in 2001, Introduction to Physical Modeling with Modelica.
Yep.
Sells for today something like $90 on Amazon, which seems little out of control to me. But,
oh yeah, believe me, it was a lot higher. So that, in fact, that's an interesting point, because I actually one of the problems what I did there was I looked at the technology. I thought, this is really nice technology, and one of the big impediments for people was the fact that there wasn't any really good documentation on it. So I wrote this book. It was the first. It was not the last, though. There are other books. So I can't say I wrote the book on Modelica, because there's more than one. But I did write the first one, and that was an attempt to sort of get people up to speed on the technology. And it succeeded and failed at the same time. It succeeded, I think, because it was written for engineers, and I think it from the feedback I've gotten from engineers who've read it, they say, yeah, this actually really helped explain a lot of these things. It failed in that you mentioned the price, and the price now is actually is much more reasonable than it had been in the past. There were times the original publication deal was inked with a European publisher, and their cost basis was in euros, and so there were some times there during some currency fluctuations where the book was selling for obscenely high prices. I mean, over $200 in some cases I had seen. This is just ridiculous.
Well, you have to question if it was actually selling at that price too.
Well, yes, exactly. And so the thing is, as the author, my motivation for writing the book was not to make stacks and stacks of cash, because I didn't. My motivation was to try and put something together that would really help people understand what I thought was compelling about the technology. And it failed in that sense, that I think I wrote a good book, but unfortunately it wasn't as accessible as I would have liked it to be. And so, and you also mentioned at the top of the show this Kickstarter thing. So one of the things that I decided to do last year was to say, look, I think it would be great if we had a book like that, but that was essentially freely available. Now, so it's a little bit more complicated than that. But what I conceived of was a Kickstarter project to say, I will write another book on Modelica, but this time it's not going to have a publisher. I'm going to publish it, and I'm going to make. And what I did was I offered a tier of support for the book that was targeted at tool vendors, and those tool vendors then essentially committed to sponsorships of the book. I mean, there were individual donors as well. I don't want to overlook them, but the big thing that I think really helped make the project a reality was that there were a bunch of corporate sponsors, companies in this area who were making tools around Modelica, who stepped up and decided, okay, we will sponsor the book in exchange for some recognition of that sponsorship in the book. And I was able to raise enough money to justify being able to spend some time writing a new version of the book that was free of any of the sort of copyright, entanglement that was associated with the previous book, and instead write a new book. And this new book, the goal will be to make a freely available version of that on the web. So this is something that, if you Google for something, you should be able to find some good documentation about the language and about the different features and the ins and outs of different features in the language, just through Google, and be able to go there. And there's also going to be the plan is to have an ebook version of it that you can put on your iPad or something, or a print version as well. And those will have some cost to them, but there will always, one of the commitments I made in the Kickstarter project is that there will always be a free version of the book that's available as essentially HTML on the web, for every version of the book, every subsequent release and everything. So that's something that I feel addresses this accessibility issue that we had with the first book.
So what was the target for your Kickstarter campaign, and how long did it take you to achieve it, or did you achieve it?
I did. So you mean target in terms of funding, you mean?
Yes.
Yeah. So originally, it's funny when you do these Kickstarter projects. I sort of read up on it, and they said, when you decide to do one of these projects, you should have a small window for people to donate. And I thought, well, that seems kind of odd. You'd think you'd want to have the largest possible window to collect the maximum possible donations, but you really do see what they were talking about when you go through this. So I originally put this up and said, okay, my funding, my target for funding would be $25K. And if I can meet that, then I'll produce this book. And I opened it up, and they said, well, it's best to have it no more than 30 days, but you can go 60 days if you want to, right? So it's a 60-day window for people to donate. So I thought, well, I don't know, this is kind of a niche area. I think I better just keep it as open as possible. So I set it for 60 days, and then I started announcing the fact that I was doing it. And time dragged on, and nothing happened, and nobody, I shouldn't say nobody, but a small handful of people donated money. And I thought, well, this doesn't look like it's going to go anywhere. It's, that nobody seems very enthusiastic about it. But the funny thing was that, sure enough, the Kickstarter apparently has done this before. And and as you got closer and closer to this date, it was like an exponential curve. It just kept going up and up and up and up. And I was just like, wow, every day I was just like, oh, there's another one. There's another one. And so this went on, and I was fortunate enough to get a number of corporate donors who, frankly, I think were getting a good deal, because a lot of them would, good Modelica documentation is a benefit to all of them. And this was a mechanism by which they could essentially cost share on the development of good documentation. And so I think, they, especially given the fact that there's also a marketing component to this whole thing, in the sense that they get recognized for their contributions. I think it was a good deal all around. And so in the end, I think, I don't remember the exact number, but it was above 40K that I ended up raising for the book. So it was like 42, 43, something like that. So it was pretty good. I mean, I think it ended up being 170% or so of the target funding level. So and it was funny because, one of my sort of a constant theme I see in a lot of things that I do is the fact that the engineering community and the sort of tech community, sort of tech in the sense of, Silicon Valley, or even just software development communities, they're so different, and they're so sort of, segregated in some ways. And so it's funny how, to me, I run into people all the time in the engineering side where you talk about Kickstarter and they say, "What's that?" And you
Mm.
go, "Oh, okay." You kind of want to say, "You know what Facebook is?" It's like, they just don't get exposed to that kind of technology uh, in their work or something. I don't know what it is. It's just some cultural difference or mentality or something that I look at a lot of stuff that's going on in technology. I think this is really interesting, and then I kind of always surprised at the lack of uptake it gets on the engineering side. And so part of my current business is trying to help facilitate those kinds of technology transfers between those different areas. But Kickstarter is a great example where one of the problems that I faced was people didn't even know what it was. They seemed like this kind of strange thing to a lot of engineers. What is this? And can I trust these people? And so on. Whereas like another one of my hobbies is playing European board games, and I get together with these guys that I play with, and they're constantly like every time we get together, they're talking about this game that has a Kickstarter project and that game that has a Kickstarter project, and how they're pumping money into all these different interesting projects that they're tracking as potential consumers. And for them, it's all part of the culture. Everybody knows what it is, and everybody's sort of watching what's going on in that space. But in engineering, we don't really have the connection to that.
Yeah, I think it's a fair point, and maybe just very briefly, we'll cover a little bit more about what Kickstarter is. I made a bad assumption there that everybody knows what it is. So Kickstarter is a crowdsource funding community, really. If you have an idea, let's say you want to make a new kind of dog biscuit, and you want to create a business around that. You could go out and ask your parents and other family members to kick in 5K, 10K to help you get this business off the ground. But that's really time consuming, really difficult to achieve. Or if you're doing, some sort of a technology product, what people will typically do is go try to find angel funding or venture capital funding to get started. And that's a job in itself. I mean, that takes a ton of time and energy, and the money ain't free. It comes with a lot of complications. And so this is a way for individuals really who have great ideas to kind of put those out there for the community to look at. The community essentially is voting on the idea, and it's smaller bets by the community. So you're not making $1 million bet. You might be one of 1,000 people who put $10 into it.
Yep. And the beauty of it is, really, to me, is that when you pledge money to these projects, the person who's creating the project has to set a limit to say, you know what, if I don't get to this level, then I'm just not going to do it, right? You don't want some anemically funded project, right? You, as the conceiver of the project, you say, look, this is the amount of money it's going to take to do it, and if I can raise that much money, I will do it. And then the nice thing about Kickstarter is the fact that when people contribute and they pledge money toward it, if the total amount of pledges doesn't exceed that the amount that the person says they need to do it, then it all just sort of disappears. The pledges are not actually charged to your card. It's like it never happened, right? And so that, to me, that's the beauty of it, because there's very little risk. You if you give somebody money in the hope of them doing a project, then you think, well, what happens to my money if they don't do it, or what happens if they're unsuccessful in raising the amount of money they need? But you don't have that issue with Kickstarter, because you don't ever, as somebody who's pledging money, you don't lose any money until they meet their target funding. And so it means that you're only going to be funding something that is likely to be successful, or at least according to the assessment of the person who put together the proposal is likely to be successful. And I think that's also a very nice aspect about it, that you don't feel like you're just throwing money at things. You're throwing money at things. You're only throwing the money at them if they have a reasonable chance of succeeding. So it's money well spent.
So you reached your funding target.
Yep.
How's the book coming?
I'm working on it. One of the things that I'm really trying to focus on in this book is making sure it's a little tricky, writing it, because I want to try and cover the language. But the funny thing that you run into is that especially if you're writing it for people who are going to be using the language, I want it to be very practical. I don't want it to be a reference manual, because that's totally disorienting. It doesn't tell you where to start, doesn't tell you, anything about context, about why you would do things. So one of the things I've tried to do is to set up a series of examples. And I mean, I've outlined the book, and I've one of the things I'm paying a lot of attention to is what examples are going to be in the book and exactly what features are they going to introduce. And then from there, making sure that the examples that I have cover all the topics that need to be covered in the book, right? So it's actually kind of complicated. I actually have these. I have a set of I have one list, which is a set of topics that I think need to be covered, and what section of the underlying specification of the Modelica language that discusses. And then I have this outline, which then goes through and sort of tries to create a thread for that, so that there's essentially a narrative that you can follow that takes you through all of these points, connects all the dots essentially. And then I have to sort of figure out examples and exactly what features will be sort of demonstrated in each example, so that we connect the dots, that there aren't any dots sort of left over at the end. And this is one of the things I learned from writing the first book was when you're trying to construct such a narrative, the problem is really disruptive. If you start writing and you don't think about it, and then you realize, oh, geez, I'm at a point here where I need to talk about something, but I haven't really laid the justification for it yet. And so you got to kind of backpedal and go back and sort of reconstruct your narrative to say, oh, and then the one more point, that I wanted to make at this point. And so one of the things I'm really trying to focus on right now is making sure that narrative is there. There's this sort of, complete thread that runs through things that covers all the topics I want to cover before I've even started writing, frankly. I mean, it's the outlining and the models. And frankly, a lot of the work is in the models. I have found, for example, I set up a blog for my company Exogeny, and I've put a lot of examples of Modelica code on there, and I've been through this experience in these sort of vignette formats, right, where I'm just doing small pieces of writing. But even then, I've had this experience of trying to start off writing something and then build the examples as I go, and I always end up having to sort of rehash things. And so now, typically, what I do is I build the models all the way through. Every point I want to make, every little feature or every little thing I want to show, I build it all the way through first, and then I thread the narrative through all of those. And that's kind of the process that I'm in right now. And so I have a lot of example models that I've built up, and I'm just sort of, like I said, working through trying to make sure that I have this complete story to tell before I actually start telling it.
Yeah. So what's the expected publish date?
I think for the Kickstarter thing, I had it as April of next year. I mean, obviously, I'm sort of also heavily involved in starting a business, so it's challenging to be able to be fast in doing this. My real goal is that there's a Modelica conference. We have there's a global Modelica conference every 18 months. The next one is going to be, I think, next March or April. I'm not really sure. And so my goal there was to hit that conference, so that the material would be available at that conference. So that's still my target. As I said, it's tough. And in fact, even on the Kickstarter project, they ask you as a creator to list risks. And one of the risks that I listed was the fact that, since I'm, it's not a full-time job and I have, this other stuff to do, I may have, it'll be, it's a risk because finding the time to do it is tricky. But I've tried to force myself to put a certain amount of time into it and make some progress. And so I'm still, trying to stay on track with that.
So yeah, you have this entrepreneurial streak to you. And as you mentioned, you're not looking for stacks of cash from, it's not easy to write a book. I mean, this is a ton of effort that you're putting into it. And so you're basically covering some of your living costs while doing that. But once that book's out there, you're not going to be making a ton of money on it directly over time.
It's like that that thing from South Park or whatever, right? Publish free book, step 2, ? 3 profit, right? I mean, it's like what's step 2 there, right? If you make a book that's available for free, what's that step that gets you to profit? I don't really know, right?
So that's where Exogeny comes in, and I've pronounced this at least 3 ways since I first saw it.
Probably. It's funny that I came up with that name because it's a term from control systems. When you talk about when you're trying to control a system, there are things that you can control. I'm going to sound like Donald Rumsfeld here. There are things you can control, and there are things you can't control. So the things that you can control are what you focus on as the developing a control system. These are things like the current or the voltage or the torque or something. Then there's other things you can't control, like the humidity of the air, or the speed of the wind or other things. So those other things are called exogenous inputs. And so this is in control systems. This is a very common term, exogenous, and it comes from. I mean, it's Latin, and exo is outside, like exoskeleton or something, and geni is like Genesis, where it's created. So it just means created from the outside or coming from the outside. So exogeny are things from the outside. So exogeny are all of these things that when you're talking about a system like a car, are the things that like the wind and the temperature and the humidity and whatever are things that you just don't have any control over. And so, but more importantly, I wanted the thing that's the sort of the focus of, if you're a controls engineer, the thing I really wanted to emphasize was just this idea of when you're in the engineering community. I mentioned there's a lot of things like Kickstarter and things that are outside the engineering community, really, and I'm sort of trying to bring those things into engineering, whether it's using modern technologies for doing version control, or modern technologies for doing modeling, or modern technologies for doing web-based services, or whatever it happens to be. But I see those things as largely outside of engineering, and so I thought exogeny just seemed like a really appropriate name for a company. Now the problem, the mistake that I made was that nobody knows how to pronounce it. And I kind of assumed, being from a dynamic systems standpoint, or background, that oh, this is a word everybody knows, and that was, of course, a huge mistake. So now I have this company who's saddled with a name that nobody can pronounce. I went so far as to put a pronunciation guide on the website, because so many people come to me and say, "Your company exogeny or exogeny," and
awfully close to misogyny too.
Yeah, and yeah. So okay, so I put the pronunciation guide. It didn't help. People still were like, I still don't know what it is. But it's just, I always tell people, first of all, imagine there's an E in front of the X, X, and then it's not an O, it's just so exogeny.
All right, so exogeny has been around for about a year now. Is that right?
Yeah, I started it in well, technically as a legal entity, I started it last summer, but I didn't really. That was just registering it with the state of Michigan. I really didn't start working full time until August.
Now, what are you offering today?
One thing that I had put out a while ago was, and this is something that I had wanted to do as a basis for some things that I've subsequently developed. And the main thing is, we have a service called FMQ. Now, FMQ is again sort of the name requires a little bit of background. There is something called FMI, and it's a technology that's sort of a sibling technology to Modelica. It's a technology for exchanging models, mathematical models, in a compiled form. So FMI stands for Functional Mockup Interface, and there's a website, fmi-standard.org. So it's also, I say it's a sibling technology to the Modelica language, but it's also a technology that's sort of shepherded by the Modelica Association, which is a nonprofit organization whose job is really just to promote these kinds of open technologies. And as I said, it's a technology for model exchange. And so in FMI, when you have a specific model that you want to run, it's called an FMU. And I wanted to develop a technology that used the cloud, in this case Amazon for FMQ, where you could build up a queue of these things. So you could take an FMU, which is this thing that you can run. It's a simulatable model, and you can get it out of a lot of different tools now. You can go to this fmi-standard.org website, and you can see all the tools that export them. But once you have them exported, I wanted an ability for people to be able to very easily just run them in large numbers. And part of this came from my experience in a previous life doing projects where you needed to be able to run a large number of simulations. And even on a quad-core machine, you're still only going to be able to really run, practically speaking, 4 of these jobs at once. But with something like Amazon's EC2 platform, you can, if you want to run, I don't know, 60,000 jobs, 100,000 jobs, you can just, fire up 10,000 instances in theory, and then just start cranking through them. And it takes you the time of running like 10 jobs, and you've got 100,000 jobs. So I thought, well, this is a really nice pairing of technologies. You've got FMU, which allows you to get these models out and be able to get them out of the modeling development environments that they're in, and then be able to just sort of throw them into a queue of a large number of jobs, and then have something just crunch on them and get you results. And so I developed that, and I sort of had a public beta of that in the spring. And that's turned out to be a sort of foundational piece in some other things that I've been working on lately. I don't have anything, really public about that, but I mean, I could talk a little bit about it. It's what the stuff that I've been doing lately has been then using this idea of being, if you can run a simulation in the cloud, and not just, I mean, it isn't important that you have 10,000 of them, even if you just want to run one of them. One of the things I've been doing in parallel with this is developing some technologies that provide really compelling user interfaces in a browser for models. And so the idea is, so I have a technology that allows me to take these models and essentially compile them into web applications. And so I can, from a given model that comes out of a tool, I can go one way, which is the client side way, which is to then develop these nice user interfaces for the browser, and then that browser application, running in the browser, can use this FMQ service behind the scenes to actually execute the model, sort of on demand. So it doesn't actually need to be running on the person's, computer, the actual model. So this is a mechanism by which people who are developing models, and this is the key thing. I found this when I was working in a lot of different applications. In is that when you develop a model, it's like your baby and you want to show it to everybody. But the problem is, in order to give it to other people, they've got to install a bunch of licenses and a bunch of software, and they got to learn how to use a model development environment and how to compile it and how to look at all the different signals and things like that. And I thought, this is a shame that it takes that much effort to sort of publicize, your baby. So I thought, well, what if we had a platform where when somebody's building a model, if they had a way to essentially, in a pretty effortless and seamless way, transform that model into an application that they could host either on an intranet or on the public internet, and let everybody use it. And every time they wanted to improve it, they could just essentially push a button, and that a new version would be rolled out, and there would be no software installation or anything for anybody. And this is all very focused on specific models. So I'm not talking about developing model development platforms or anything like that. I mean, I'm just talking about taking a given model and being able to just make it accessible to people, and allow potential users to get the most benefit from it without having to go through the sort of hassle of installing a lot of software and things like that. So FMQ is a sort of, like I said, general service that we offer, but then there's also work that we're doing with customers now that is helping them with this other process I talked about, which is taking their models and making them more readily accessible, so that when they invest the money in building up these really good models, that they have a maximum impact by getting them out to all the people who could really benefit from that knowledge that's captured there.
Yeah, that sounds really exciting. I wish you well with that. Michael, hey, I really appreciate you coming on the show today. It's been enlightening. If people want to find out more about you, NAMUG, is that what you call it? NAMUG? North American Modelica User Group?
So there's the North America Modelica Users Group, and the website is na.modelica-users.org. So not doesn't exactly roll off the tongue, but it's an attempt by the Modelica Association is trying to keep all the different users groups under a single domain just for sort of consistency. So it's NA and then dot, and then the other thing that's consistent across all of them is this modelica-users.org. And then for the company, it's www.xogeny.com.
And since you know what Kickstarter is, I assume that you're out there to some degree on social media as well. Where do people find you there?
Yep. So Twitter, it's XOGENY. That was another great thing about that name, Exogeny, is that it was in the Google space and Twitter space. It was largely unoccupied, so there were no squatters on it. So the main thing, I guess, would be probably Twitter. I try and put a lot of the sort of company announcements, mostly blog stuff and things like that. Stuff I find interesting out on that feed. So, like I said, XOGENY. I don't really use the Facebook and Google Plus kinds of avenues just yet. I think for most of the interactions I have with customers are pretty sort of at a kind of personal level, and so I think the Twitter stuff actually fits my I don't know, my sensibilities well.
All right. Well, great. Yeah, I wish you luck with the new business, and look forward to the book. I'm probably going to be one of these real weird few people in the world that is looking forward to reading it.
And you'll be able to.
That's all for this episode. Thanks for listening to the Life Upfront Engineering Podcast. Visit lifeupfront.com to comment and connect with me on Twitter, Google+, and LinkedIn. Also, you can really help the show by leaving a review on iTunes. Thanks again. Until next time.